Okay, composition of functions. So generally, when we talk about composition of functions, the notation that is used is something like f with an open circle of g, and that's how it's verbally expressed, f of g. Sometimes you'll see it with more of a function notation like this. It can also be written as f of g of x. All of those things mean the same thing. I mean, in terms of what it means with the actual function, if we have, let's say, a mapping that we're going to call f, so that's our function, then this is the domain of f, this is the range of f, and f would take an element in its domain and to the range, and so we would call it f of x. Well, in a composition of functions, then let's say we have another function, maybe g, and let's say that this is the domain of g. Maybe I'll change colors to make that more explicit, right? So this is the domain of g. Let's say that this is the domain of g, and then let's say that this is the range of g. So here's our g function. So it's going to take the element, let's say it takes f of x, and it maps it to the range. So this would be g of f of x. So we would say that, again, g of f of x is the composition of functions. So this could also be written g of f or g of f of x. So notice it's actually backwards from the mapping because you're applying g to f of x, that it's actually composed g of f. If we wanted the composition f of g, then we'd actually start with the g function. So if this was g, that would take, some element x to g of x. And then if we took, a new function f would take g of x to the range, which would be f of g of x. So again, you can kind of see how that works. Algebraically, you're given two functions. Like let's say f of x is equal to maybe x over x plus 2. And we'll say g of x is equal to 3 over x. Find f of g. Well, I always use the more explicit notation. So to say f of g of x. And then I just need to replace g of x with what g of x is. So really what I'm finding is f of 3 over x. And what does that mean? That means I go to the f function, and anywhere I see an x, I replace it with 3 over x. So this would be 3 over x over 3 over x plus 2. So this is the composition function. I can certainly simplify this, but if I'm being asked to identify the domain, I want to think about what we talked about in the combining functions video, that I really need to think about all of these denominators so I can really identify what needs to be excluded. So clearly here is a denominator, so we undoubtedly have to exclude 0. Here's another denominator, which would exclude the same 0, but then this is also a denominator. So is 3 over x plus 2 ever equal to 0? And how would we figure that out? Well, solving this equation, we would have 3 over x is equal to negative 2. So now I'm just going to kind of think of negative 2x is equal to 3. So that would be when x is equal to negative 3 over 2. So that would be the number that we would have to exclude from the domain, because when x is equal to negative 3 over 2, we would get a 0 in this denominator. So x can't be negative 3 over 2. So those are the two numbers that need to be excluded from the domain. So negative infinity to negative 3 over 2, negative 3 over 2 to 0, and 0 to infinity. Now we can think about simplifying this or just making it look a little bit prettier. So to simplify this, we have 3 over x. I would get a common denominator in the denominator. So we could say that this would be 3 over x plus multiplying this by x over x. We would have 2x over x. So this is 3 over x all over 3 plus 2x over x. So now taking the 3 over x numerator and multiplying it by the reciprocal of the denominator, that x factor will cancel, and I'm left with 3 over 3 plus 2x. So that's my composition function simplified. But notice, if you simplified it before considering the domain, you would have missed that 0 that has to be excluded.